All right. Welcome to Interconnection Networks, how we can learn more about our current environment that we live in, how we communicate with each other, and how this communication has completely changed the way computers work and interact with individuals. My name is Mick Zeller. I'll be basically guiding you through how networks, some of the basics of networks and how they're designed, at least the really big items. Now, a preface before we get going, the information that I learned here has really changed my views on how computers interact with each other. As you read in my paper, going over the introduction of the supercomputer and just how it could compile and solve just complex information for those scientists and the engineers, to the cluster computers. It's brilliant. Think of those cluster computers, a bunch of individual nodes linked up by a backbone of communications. Their raw computing power is all combined to become essentially a supercomputer. There's a couple limitations, such as the time that it takes to communicate from one computer to the next, and the parallel programming is an issue that software developers and the engineers who design those networks work on. But it's just amazing to be able to see how these computers are able to speak essentially just with each other. Some of the characteristics that we have to consider in creating a network fall on the distance, the speed, the topography, or the design of the given network. And then, of course, the shared lines. Now, what is that shared line that I'm talking of? Essentially, when it comes to parallel computing, you have gates or switches that connect various nodes to each other. Shared lines is a way that cuts down on the cost of creating a network, but it does run into trouble of conflicts, stalls, and just huge delays just of information. If two pieces of information which are going bidirectionally, so one's going forward, one's going backwards from different nodes, and they run into each other on the port, there can be a real collision there that's a hurdle for these software engineers to overcome. Now, the network essentially can be broken up into a couple different pools of communication. There's the typical LAN network, which is a local area network. That broadens up into a WAN, or a wide area network. You can think of this network just as the internet that we log on to each and every single day. This picture that we have here of Google essentially just shows site traffic for various websites in relation to other web domains. But yeah, let's just go on to the next slide. So in 1984, the Open Systems Interconnection came out with a simplified and standardized way for creating and implementing networks. These were suggestions that essentially allowed various networks to communicate with each other. Ones that were incompatible before that period of time became compatible with this network. The idea behind it essentially is that packets or pieces of information are passed from one location to the next with really no distinguishing identity of what the data is. Now, The benefit of that is when you have two networks that aren't able to connect with each other, if all it knows is where the information needs to get to, the information doesn't get caught up in all the hurdles and issues of incompatibility. One of the really cool things in this book is it talks about basically two generals just on a battlefield needing to communicate with each other. They're divided by like a valley, and so General A takes a letter, he puts it in an envelope, and he addresses it to General B. But General A, there's no way he's going to walk over there and give it to the other general. He has a lot more important things to do, so he hands it to a lieutenant. That lieutenant says, okay, well, this needs to go to the lieutenant under General B, and then he'll pass it up the chain of command to the general. Lieutenant, same deal. He doesn't have the time to worry about going and delivering it, so he passes it on to a sergeant, who in turn writes another sergeant's name that's under command of General B. That sergeant hands it to a private. The private gets on a motorcycle, and he drives over to Camp B, and he gives it to another private that's under Camp B. That private follows the chain of command up to the general. The general opens the information, and as far as the general knows, he got a letter directly from General A. There's really no knowledge of basically the path that it followed to get from one general to the next. Now this is, it might be somewhat of a silly analogy, but in reality it's actually very applicable to how these protocols work in practice. This is a general view of some various networks. From left to right, we see the client server, the peer-to-peer server, and the grid architecture. Grid computing is how I refer to it in my paper. The client server, you can think of it as a centralized hub with a large computer. Basically, the clients log into that computer just over the network, and they're able to access the main central hub's computing power. The peer-to-peer guide is typically what I think of with peer-to-peer guide is torrents, and in a lot of ways that's exactly how it is. Essentially, it's a bunch of computers that are connected over a network with no real absolute design. There is a piece of software that basically allows each peer to be able to upload a portion of packets, and those packets are interpreted by another peer and combined from other packets that he receives from other computers into a program. The grid architecture is amazing how they thought it up. Essentially, what they decided is there were a lot of computers that were sitting idle in people's homes. When they went to work or on vacation, the computer was on, but nothing was using the CPU or the storage capabilities. And so what was developed was basically an interface that allowed these various computers to connect to one another and use the combined computing power to solve a task. It's really similar to cluster computing, only it's with individual computers. They call it heterogeneous computers, so different specs, different CPUs, basically just all connected with a similar interface. Now, some of the limitations when it comes to this parallel computing, which is present in cluster computing as well as the grid computing, can really be boiled down to kind of a thought experiment that the text had just in the examples at the end of chapter 6. The idea behind it is you have 5 different philosophers that are sitting at a round table. These philosophers can do one of 2 things. One, they can eat. The others think. They do need both chopsticks to eat though. Now, the issue is there's only 5 chopsticks, so when a philosopher needs to eat, there has to be a certain way for that philosopher to know that his fellow philosopher to his left or his right isn't using his or her chopstick. What it all boils down to essentially is a queue, a priority queue, with a centralized location that basically tells when to pick up the information, or when to pick up the chopstick and when to put it down. But it's a really cool example of visualizing how software engineers and hardware engineers overcome the challenge of parallel computing. These 2 diagrams here are just topographies of the Omega network. The benefit of an Omega network is you don't have nearly as many switches that connect various nodes to each other, so you save money just by not having to deploy a bunch of switches. The downside is if one of these switches receives a command, like say for instance 1B receives 2 commands at the same time, it causes a collision, and this can be really bad. So another very more expensive way, but it doesn't have those collision issues, is in the next diagram. Essentially, what that is there's a switch for each individual node, thereby eliminating the possibility of a collision or occurrence. And it slips my mind, I cannot remember the name of it, but the scalability isn't as possible as the Omega structure, just because of the increases of switches. For each switch you have to have, or for each node you have to have 2 switches essentially. This is just a visual representation of various combinations of switches and how we can gain information. In my paper I discussed the creation of these warehouse scalable computers that companies like Google and Amazon and Facebook use, that are multiple servers that are connected to each other to serve a primary goal. Basically, in order for anybody to be able to access those, they have to go through that wide area network. The WWW, as most people think of it as. Essentially, information is passed through a router, which is like a localized piece of equipment that distributes the information through various switches and to your end computer. The switched Ethernet is just an example of how a switch is used for certain priority communications. And in the bottom, it's a representation just of Wi-Fi. Wi-Fi is very common today just because of its convenience of less cords. Essentially, what it relies upon are frequencies that data piggybacks on from point A to point B being your device. With Wi-Fi, there's 2 standards that have been put in place, the 2.4 gigahertz and the 5 gigahertz spectrums. The lower the number is on those spectrums, the more wide the waves are. That wideness allows for the signal to be able to travel further and penetrate surfaces better. One example that my dad told me was like a really low noise. If you hear like a bear growling in another room, you're probably going to hear it. But then he mentioned like whales. They have a really low pitched sound. It travels all across the earth just because of that. But those higher frequencies, one advantage is they are able to, because the waves are much closer together, they are able to carry more data faster to a location. Disadvantages, though, because they are closer together, they don't have as large of a footprint. He similarly made the comparison of like a high-pitched screaming sound. It really doesn't penetrate too far, and so those are a couple different ways to think about Wi-Fi. Now, why does all this matter? What's the point of the network and focusing on how the network can be of advantage to us? Just according to S&P Capital IQ, it's a very trusted financial magazine in the IT sector, the information and technology sector. The fastest growing services are in the software and services location. Think of the software as service, like in the paper, such things as like Google Drive or Dropbox or Adobe Creative Suite. Basically, there's a centralized location that is able to hold information, and it distributes it through the network. The other areas of the IT sector, the technology, hardware, and equipment, cases of that would be like a cell phone or like a Wi-Fi router, or a Wi-Fi router, or like a modem would be in that. Semiconductors and semiconductor equipment would just be for like computers or really technical chipsets. But the reason why we need to be focused on this is it is the way of the future. I'm convinced of that, especially after doing this assignment. It makes so much more sense, not only on like an economy of scale perspective, but just on the implementation of a really diversified network to do it in these cluster computer formats. But thank you again for watching this video. I hope that you learned something from it. I really enjoyed it. If you do have any questions, feel free to contact me, and I'd be more than happy to answer them. Thank you, and have a great day.